So it's going to be important that you guys get involved with this. So if I start asking you questions, feel free to chime in and tell me what you think, okay? So previously we talked about at a high level what a deterministic finite automaton is and how it processes. We gave the formal definition of a DFA. We talked about how it might process a string. We also seen an example, and we also seen how we can represent DFAs through the formal description, a transition table, and of course a transition or state diagram. So I thought it'd be meaningful for us to kind of go through some examples of designing DFAs and some trickery that I would suggest here or there when we're thinking about these things. And by no means is there like one way to do this. This is arguably one of those fun creative tasks when you design a machine. And this is one of the fun things when you're studying automata theory, when you really start playing around with the machines and you're like, oh, well, cool. I don't actually have to like physically build the machine. I could just, the machine, it works on paper. I can literally walk it through. So I thought we would do some examples so that way we can play around with this a bit. So let me just getting ahead of myself. Okay, let's start with this first scenario. So for our first example, let's talk about accepting binary strings. Accepting binary strings with an odd number of zeros. So I want us to think about this. Now for those that need to kind of lay out a couple definitions for you, we say a number is odd if it has the following form. So when I'm counting up the number of zeros in the string, it has to be that frequency, how many times it appears, has to take the form of 2k plus 1 for some integer k. So you'll notice quite quickly if you put in k as 0, you'll see that this ends up just being 1. Put k as 1, you get 3. K as 2, you get 5, and so on. So what I want to do is I want to be able to take any binary string, and I would like to know if it has an odd number of zeros in it or not. Does everybody understand the problem? So I want a DFA that recognizes that language. So I've laid out to you a decision problem that we need to come up with a DFA. It needs to accept whenever there's a binary string with an odd number of zeros and reject whenever there is an even number, right? Because that's the other possibility. So I have some ideas for how we might go about this. Now, I don't know if you have any ideas in the chat. Just please tell me if you have any ideas. Let's see here. So knowing that there's either going to be a state for which there's going to be an odd number of zeros and then there might be an even number of zeros, it might be a good idea to maybe have two states. That might be a good place for us to start. Maybe I'll make a picture. Let's make a picture. Let's go with the transition diagram. I think that's a meaningful way we could start with this. And then, of course, we'll see what it looks like as a transition table and its formal description too. That way we can get a grip over these definitions. So why don't we make a transition diagram? Maybe that's a good place for us to start, just because we know how parity works. There's even or odd, right? So I would like to get it so that maybe I start off in some state. And I have two states. I have Q0 and Q1. And I would like it to be that all the binary strings with an odd number of zeros go into Q1. So when I finish reading the input, I want the DFA to be in state Q1 if there's an odd number of zeros. Do you see where I'm going with this? So anything that is not that is going to be sitting in Q0 when we're done processing the string. If it has an odd number of zeros, we want to make sure it stays in Q1. So notice it could either stay in Q1 or it has to get out of Q1. What characterizes that? So you can imagine this. Imagine I have a string. like this. If I give you a string like this, it has an odd number of zeros in it, right? It has 1, 0 in it. But notice I have a whole bunch of 1s that come after it. Do those 1s matter at all? Yes or no? They don't do anything, right? These don't do anything. So as soon as I'm reading this, so you can imagine this as a process for which I'm reading each one of these, and I'm keeping track if it's odd or even number of zeros. So the minute I encounter another 0, like if another one appeared like this, you know right away, oh no, this better not be in Q1 if that happens. But if another one comes along, oh yeah, I better be in Q1 if that's the case. So do you notice that the 1s really don't matter a whole lot? They just don't. So it's just like if I were instead going to just ignore the 1s and just read the zeros. But we need some way of characterizing this. Do you see what I'm talking about? What really matters in the string are these zeros, not the 1s. So here's an idea. We don't care about those 1s, so I'm just going to make it so that no matter which state I'm in, I'm just going to stay in that state if I read a 1. Seems rather intuitive, right? They don't matter. I just need, if I run into them, I better stay in the same state because I'm trying to keep track if the number of zeros is even or odd. Does everybody see what I'm talking about? Yeah. So what happens? So when I start off in Q0, if I read a 0, I have an odd number, right? So when I have an odd number, it brings me over to Q1. If I read another 0, where does it put? Should I still be in Q1 if that's the case? Should I stay in Q1 if I read another 0 upon reaching into Q1? No, right? Right? No, we don't want to stay in Q1 because that means there's an even number. So here's the design idea that I have in mind. So you think of me like the Wizard of Oz, I'm behind the cloak thinking about how I could design this thing. So we can have as many 1s as we like. But the number of zeros to reach the final state is exactly equal to 2k plus 1. And of course, that's odd, right? Not odd in like me, yeah. I mean like the number. So now I should label these with 0 then, right? And then now I have defined the transition function. So now if you take a look at my string, this is just one example. So this is one possible input, an instance, you could say. So I recommend when you're first playing around with this idea, you take a few strings out, see if it makes sense. And in fact, you can almost go through a process like debugging your machine by just giving it some strings like this. So if I'm in 0, I read a 0 from Q0, I go to Q1, stay in Q1, stay in Q1, stay in Q1, stay in Q1, go to Q0, go to Q1, and I have an odd number of zeros, boom, I accept it in Q1. So I encourage you to take out some more strings and try it out. But let me just make sure I'm clear with everybody. I should define as well this DFA formally. So that way, this is the transition diagram. So I can also define it like this. So I'm going to call this machine modd. It's going to be this one, but it's actually defined like this. DFA modd is going to be equal to Q sigma delta Q0 and F, where where Q is equal to Q0, Q1. Sigma, or the input symbols, are going to be equal to 0 and 1, like this. The start state is Q0. And F, the state of accepting states, or final states, is Q1. And you'll find very often, rather than describing all of those delta terms like explicitly, the formal definition you would give delta in its complete form, as per I did. But you can also replace that with the transition table too, right? So I'm going to use the transition table. And delta as in its transition table. Which, now let's draw the transition table. It's nice and small. 0, 1, because those are my input symbols. I have two states, Q0, Q1. Q0 is a start state, Q1 is the final state, so I'm just going to label them accordingly, where Q0 is the start state, Q1 is a final state. I indicate them with the star. So to go to Q0 to Q1, on 0, it goes to Q1. On Q1, when I read a 0, I go back to Q0, right? And on a 1, I stay in my same state. And there you go. There's the transition table. And there we go. So now I have not proven to you that this is a correct DFA that indeed recognizes the language of all binary strings with an odd number of zeros, but I think this example illustrates how you might go about it. Most certainly, you'll notice that there's a few cases here. In fact, eventually I will prove for you that this DFA is correct, but not today, not today. Are there any questions about this DFA? So you could just straight up use this and it will tell you, yes, it has an odd number of zeros, or no, it does not. So I will tell you that it is correct though. Like, this is correct. This is a correct DFA for this. It will recognize such a language. I know, right? Some spooky stuff. Now, let's do another example. Let's get another example going. Actually, I have a little bit of a conceptual question. Let's think about, I want to think about something a little different. This is a question more for discussion. Can a DFA accept the empty string? Now, I must stress, the question is actually a fairly broad question. Some DFAs, the answer will be yes, it will. Some, it may not. But can a DFA accept the empty string? Can one? And I kind of answered it for you, right? But why or how? So if ever you needed to accept the empty string, there's something you could always do to accomplish this. But I'll give you the easy way of approaching it, but most certainly there's a lot of ways to go about this. So just please recall the empty string epsilon has length 0. But remember, a DFA will either accept or reject upon reading its input. But this string has length 0. So what does it do then? So what's it do? So no transitions will occur because it's not, there's no symbols to read, right? So question, I want to accept the empty string. What's one thing I can do for a DFA? If no transitions occur, any suggestions? So remember, what's happening is I give you the DFA. It starts in the start state, and then it doesn't do any transitions, and it either is going to accept or reject what state, depending on what state it's in. What's something I could do to ensure that epsilon gets accepted? I'm not saying that it won't cause any other issues if your other strings rely on this state or something, but I'm saying that this is something you can do. Well, think about it. Since it does no transitions, because there are no symbols, right? It's still in the start state, right? So what can you do to that start? Like, what should be included in the final states? What should be included in the final states? Correct. You're correct. That's exactly it. Exactly it. You make the start state a final state or accepting state. If you make a start state a final or accepting state. Boom. So if you ever need the epsilon to be accepted or the empty string, just keep this in mind. This is one of those edge cases with the DFA. So you have to be careful as well. If you put the final state actually just straight up on, you make the start state a final state, you have to watch out, because if you're trying to expect a string that isn't actually the empty string, be careful for that, okay? So if you don't want to accept the empty string, don't make the final state a start state, okay? So just be careful with that. Now, let's consider another example. So let's head over here. So remember that when we talk about DFAs, our goal typically is to accept strings of a language. Previously, we talked about the language of binary strings that have an odd number of zeros. You could describe this formally. You could do this with all sorts of languages, and that's expected, right? If you can mathematically formalize it, you're generally fine. The question is, can you design a DFA that does that? So, just as an example, let's consider another language. We're going to try to design a DFA for a given language. Suppose I want to design a DFA that accepts strings of the following form. They're going to be x, 0, 1, y. So x and y in here are any strings of zeros and ones. So this string has a very particular form. You can also describe it in a different way. Here's another way I could describe the same set of strings to you, or language to you. It's W, and I must stress that we're going to be talking about the binary strings. So it's going to be a string such that W has the form x0, 1, y for some strings consisting of zeros and ones. So these two are actually just two different ways of describing the same set of strings, the same languages. So sometimes it's helpful to think about one language and be like, okay, well, what does that actually mean? Well, it looks more like this. So this is more like the form you might be more familiar with, where we given the string, it has some alphabet, and this is what it would look like. So you might think of, damn, what the heck is this? Like, what does this look like? Well, actually, what we're actually describing with this example is trying to detect a substring. So for those that aren't acquainted, a substring, if I give you a string, a substring is a string that is found and contained within another string. So in this case, the pattern for the substring is a 0 immediately followed by a 1. So any string that has this pattern in it is in this language. That's what this says. So what we're trying to do is actually detect binary strings that have this substring. So we're trying to detect the substring 0, 1. So if we can do that, we're okay. So the minute you identify that is as follows. So I'm going to give you a common trick for how you might deal with something like this. So here's a common trick. Not saying that this is what you must do, but this is most certainly a trick. Is contain a path. So we're going to make a pathway in our transition diagram. Contain a path with the substring, where other transitions on states are used to manage exceptions to the substring. That is, remember, all we need is just to encounter the substring, and then we're okay, right? We just got to make sure that if we run into anything else after the fact, that we're not interfering with this process of detecting 0, then 1. The minute you see that, this becomes actually a pretty easy task. So since the substring actually has only 2 symbols in it, I'm going to make an initial start state, Q0. And then what I'm going to do is I'm going to, because remember, my pattern has 2 symbols in it. So if I'm starting in Q0, I'm going to need 2 more states. One for upon reading a 0, and then another for reading 1. So this might be a natural thing to try. So Q1, Q2, but you know right away that I'm going to need that pattern somewhere in here, right? It has to go 0, then 1. See, 0, 1, there's my substring right there. So if I can get from Q0 to Q2, I'm good. But remember, there's all sorts of other stuff that can happen too, right? So I have to be careful. Also, another issue is strings that look like this. All this stuff doesn't really matter. The point is that 0, 1's right here. That's the first time we run into it. But the thing is, there's a whole bunch of zeros that come before it. Do you see that? So I need to make sure I take this into account as well. So notice that whenever I read a 1, that's definitely not reading 0, 1, right? But the minute I see a 0, I got the first symbol for the substring. So that's the first symbol, right? But I may be potentially reading in more zeros. So I'm going to include a transition when I read 0, like this, until I potentially see a 1. When I see that 1, then I've read the pattern. But anything after that can happen, right? I don't really care whatever stuff comes after. There's just a bunch of... It doesn't matter what's after this, right? Does everybody see that? So here's a DFA that actually does it will recognize this language. But yeah, no. So you'll notice quite quickly that so this will just read in the 0 and 1, and it will able to be handling more symbols if they were to appear on the left side of it and the right side of it. Are there any questions about this example, or is this pretty darn good? So this is a common technique you can use with a DFA, is you embed the pattern in your DFA. So you make a pathway, you contain a path with the substring, where all of the transitions are handled such that you're ensuring that this pattern gets read if it is going to successfully get here. Think about it like an obstacle course. So let's take this idea then. I don't see any questions, so let's proceed. Let's take this idea and just drag it to its more a different kind of application. But it's very much the same idea. So let's consider, in one last example, let's try to compute, sorry, not compute. I get really excited about this because you could take all this stuff and think about it in all sorts of different ways. But when we think about automata like this, I would like to design the DFA such that it recognizes the language, but I always like to take advantage of the internal structure, the specific or particulars of that language. Just like when you try to solve a problem at a higher level, for a problem, I design the algorithm to exploit the properties of that problem. It's the exact same exercise. So let's consider another one. Let's consider, so I'm going to call this at least 3 ones. So what I want to do is I want to come up with a DFA. So let's design a DFA that recognizes binary strings with at least 3, well, I'll write the word because it gets a little bit strange when you don't, 3 ones in them. So just to be clear, what I mean by this is that a string like this, that's okay. A string like this, that's okay. A string like this, that's also okay. All 3 of these are okay. However, this string, not okay. Having 2 ones and a 0, that's not enough ones for me. A string like this, there's no ones in this. Not okay. We need to reject those. Is that clear, everybody? So we're going to take the same idea that we had previously. Remember, we can almost think of the same process where we have our target of I need at least 3 ones. But you can think of it like I need to detect 3 ones, but now I don't need them to actually be in the case where one has to immediately follow the other. It's just that they have to appear. So you can think of it like a loosening of the same design strategy. So here we go. So you could use the same idea. So I have at least 3 ones, so I'm going to make a pathway with 3 ones, because I need at least 3 ones. So I'm going to make a start state, call it Q0, Q1, Q2, and Q3. If I can see at least 3 ones, right, then I'm good. Doesn't matter whatever follows after that. As long as I see those at least 3 ones, we're okay. So I have a question now. I haven't entirely defined the transition function, though. I just told you that if you see a 1 here, you go there. If you see a 1, you go there. If you see a 1, you go there. I'll give you a bit of a tip here. Let's see here. Let's see. The final one, remember I just told you I don't really care what happens after here. But what should I do for the transitions on Q0, Q1, and Q2? Any suggestions on what I should do with these three here? Because I need to define a transition when I read 0. Do I do something quite like that over there, except I don't have a 1 in there? Because remember, for each symbol, I have exactly one defined transition on a given state. I can't have multiple ones. I can't be in Q0 and Q1 at the exact same time. That I can't do that. Well, remember, I only care about the 1, so if ever I see a 0, I just stay in this current state, right? And boom, there you go. So notice that if I try any one of the strings I have over there, notice that whenever I see a 0, it doesn't matter because it doesn't accumulate our count. You can imagine going along this pathway is like keeping a count of how many I've seen so far. And this is you'll notice quite quickly when you're dealing with a DFA like this, since the only thing we know at a current time is the current state, we have limitations for what we can remember. We have a limitation of memory. We don't have any other place to put things, so we can use states to help us remember where we are. But remember, there's a finite number of them. So just keep in mind, actually, I'll just summarize what we just did here, just to give you an idea of how this all came together. So the design idea here is we have a path of vertices where each is a state for when one symbol 1 is read. So naturally, the path is of length 1, 2, 3. The path has length 3. Length 3. So at least 3 1s are read. Then we permit any other symbols. Right? Now I have a question for you. So now that you understand how we can do this with at least 3, what would I do if I wanted to have at least 4 1s instead of at least 3 1s? Are there any suggestions for what we can do with this? Any suggestions at all? And you don't have to get very particular about what states there are or anything like that. Just tell me the big overall concept idea. So remember, all I had here is I have a path of length 3, each one with 1s on them. This guarantees I'm going to have to read at least 3 1s to get over to Q3. So what would I do if I wanted to get at least 3 1s? Sorry, at least 4. At least 4 1s this time, instead of just 3. I would do what? So in our idea is I have a path of vertices or states. Yeah, add another one, exactly. You just add another state in here. You just put another, just jam it right here. And you're just like, I'll call it Q blah. Put 1 there, put 1 there. Put a loop here with a 0, and there you go. This will accept binary strings with at least 4 1s. Very nice, very nice. So these are a few examples of designing DFAs. I must stress, remember, we have not proven that these DFAs are correct, but most certainly I find that when you describe the DFAs, especially when you describe them state by state and the reason why they're there, it's very helpful for informing somebody why it's designed the way it is. This isn't the same as mathematically proving that it is correct, but most certainly it's intuitive. So that's all I have to say about DFAs at this point. So I say thank you so much, everybody. That was DFAs, at least at a high level.